Testing bipartiteness, an application of breadth-first search. Recall the definition of a bipartite graph. It is one where the node set V can be partitioned into sets X and Y in such a way that every edge has one end in X and the other end in Y. To make the discussion a little smoother, we can imagine that the nodes in the set X are colored red and the nodes in the set Y are colored blue. With this imagery, we can say a graph is bipartite if it is possible to color its nodes red and blue so that every edge has one red end and one blue end. The problem: in the earlier chapters, we saw examples of bipartite graphs. Here we start by asking, what are some natural examples of a non-bipartite graph? One where no such partition of V is possible. Clearly, a triangle is not bipartite, since we can color one node red, another one blue, and then we can't do anything with the third node. More generally, consider a cycle C of odd length, with nodes numbered 1, 2, 3, and so on until 2k plus 1. If we color node 1 red, then we must color node 2 blue, and then we must color node 3 red, and so on, coloring odd-numbered nodes red and even-numbered nodes blue. But then we must color node 2k plus 1 red, and it has an edge to node 1, which is also red. This demonstrates that there's no way to partition C into red and blue nodes as required. More generally, if a graph G simply contains an odd cycle, then we can apply the same argument. Thus, we have established the following. 3.14. If a graph G is bipartite, then it cannot contain an odd cycle. It is easy to recognize that a graph is bipartite when appropriate sets X and Y, i.e. red and blue nodes, have actually been identified for us, and in many settings where bipartite graphs arise, this is natural. But suppose we encounter a graph G with no annotation provided for us, and we would like to determine for ourselves whether it is bipartite, that is, whether there exists a partition into red and blue nodes as required. How difficult is this? We see from 3.14 that an odd cycle is one simple obstacle to a graph being bipartite. Are there other more complex obstacles to bipartiteness? Designing the algorithm. In fact, there is a very simple procedure to test for bipartiteness, and its analysis can be used to show that odd cycles are the only obstacle. First, we assume the graph G is connected, since otherwise we can first compute its connected components and analyze each of them separately. Next, we pick any node S in V and color it red. There is no loss in doing this, since S must receive some color. It follows that all the neighbors of S must be colored blue, so we do this. It then follows that all the neighbors of these nodes must be colored red, their neighbors must be colored blue, and so on until the whole graph is colored. At this point, either we have a valid red-blue coloring of G, in which every edge has ends of opposite colors, or there is some edge with ends of the same color. In this later case, it seems clear that there's nothing we could have done. G simply is not bipartite. We now want to argue this point precisely and also work out an efficient way to perform the coloring. The first thing to notice is that the coloring procedure we have just described is essentially identical to the description of BFS. We move outward from S, coloring nodes as soon as we first encounter them. Indeed, another way to describe the coloring algorithm is as follows. We perform BFS, coloring S red, all of layer L1 blue, all of layer L2 red, and so on, coloring odd-numbered layers blue and even-numbered layers red. We can implement this on top of B of S by simply taking the implementation of B of S and adding an extra array color over the nodes. Whenever we get to a step in B of S, where we are adding a node V to a list L of I plus 1, we assign color of V equals to red if I plus 1 is an even number, and a color V equals to blue if I plus 1 is an odd number. At the end of this procedure, we simply scan all the edges and determine whether there is an edge for which both ends received the same color. Thus, the total running time for the coloring algorithm is big O of n plus n, just as it is for BFS. Analyzing the algorithm, we now prove a claim that shows this algorithm correctly determines whether G is bipartite, and it also shows that we can find an odd cycle in G whenever it is not bipartite. 3.15. Let G be a connected graph, and let L1, L2, and so on be the layers produced by BFS starting at node S. Then exactly one of the following two things must hold. 1. There is no edge of S joining two nodes of the same layer. In this case, G is a bipartite graph in which the nodes in even-numbered layers can be colored red, and the nodes in odd-numbered layers can be colored blue. 2. There is an edge of G joining two nodes of the same layer. In this case, G contains an odd-length cycle, and so it cannot be bipartite. Proof. First, consider case 1, where we suppose that there's no edge joining two nodes of the same layer. By 3.4, we know that every edge of G joins nodes either in the same layer or in adjacent layers. Our assumption for case 1 is precisely that the first of these two alternatives never happens. So this means that every edge joins two nodes in adjacent layers. But our coloring procedure gives nodes in adjacent layers the opposite colors, and so every edge has ends with opposite colors. Thus, this coloring establishes that G is bipartite. Now suppose we are in case 2. Why must the G contain an odd cycle? We are told that G contains an edge joining two nodes of the same layer. Suppose this is the edge E equals to xy, with x and y in Lj. Also, for notational reasons, recall that L0, layer 0, is the set consisting of just S. Now consider the BFS tree T produced by our algorithm, and let Z be the node whose layer number is as large as possible, subject to the condition that Z is an ancestor of both x and y in T. For obvious reasons, we can call Z the lowest common ancestor of x and y. Suppose Z is in Li, where I is less than j. We now have the situation pictured in figure 3.6. We consider the cycle C defined by following the Zx path in T, then the He, and then the Yz path in T. The length of this cycle is j minus I plus 1 plus j minus I, adding the length of its three parts separately. This is equal to 2 times j minus I, then plus 1, which is an odd number.